recording here. Okay. Luckily, I made a note to myself. Pick up here on Tuesday. Wow, nice. Score. How about we do a little bit of review before we actually pick up there. Like I said, you might need, if you don't have your formula sheet, you'll need to come grab one because we're going to be using it. And isn't that reason enough? Last day we started the chi-square goodness of fit testing. It's our first new distribution that we've seen, or first new continuous distribution that we've seen besides the Z distribution. So before we were just using the Z distribution and that was awesome. We knew how Z worked. And so now we need to get to know this new distribution called the chi-squared. And so we started with the chi-squared goodness of fit testing, and we'll see if we have time for the next chi-squared test. The chi-squared test for independence is the next one that we're moving into. I'm willing to take it a little bit nice and slow here because it's our new distribution that we're still getting to know. And what I did, instead of printing a huge table, is I just made a condensed version of it. And so on your formula sheet. And so I'm going to bring both these guys in here. And once we know the chi-squared distribution for the goodness of fit, what's really nice is we're going to end up in the same scenario that we did for Z. We can apply the same distribution, but for a different type of question. And so once we know the distribution, then that's kind of half the battle. More than half, maybe. So on your formula sheet, you have these two. Okay. And so, well, this is the first time that we see this degrees of freedom. This degrees of freedom, or the idea behind degrees of freedom, is going to come back to haunt us. This is a first year stats course, obviously. And so we're not going to talk about what it is. That's more for kind of second year, third year stats courses. And so for us, we just need to know that they exist and that we need them to figure out the shape of the chi-squared distribution. And I should call this review, I guess. Oh, that's what it was. I knew I had some admin. Which is like housekeeping, right? On Tuesday, after the long weekend, I'm going to just post a video for you guys. So no class. Is that okay? Got some thumbs up, got some smiles. Cool, awesome. So that's the Tuesday after the long weekend. And so here, note, Tuesday, November 12th. So that's next Tuesday. We're going to do video only. Watch at your leisure. Obviously, watch it before the Thursday, but I just can't. And I think that's okay. Everyone's kind of swamped still with other things, I know, at this time of the year. So my other class that I had this morning, they're like, oh, good, because I have a test that day anyway, so that's fine. And so there, I nearly forgot. So I'll post a video. Depends on how far we get this week, and then I'll kind of pick up from there. And so I've got a a bank of video. I've got so many videos, especially on this stuff. So it'll be something from there. Probably starting one sample means, but we'll see. Okay. Good. That was important. I'm glad I didn't forget. Now let's get back to the review. So first thing we talked about, or maybe not the first thing, but the idea behind the chi-squared is, okay, the degrees of freedom determines the shape of the chi-squared. Okay. And the degrees of freedom, it's driving me bonkers. Determines the shape of the chi-squared. So that's a Greek letter chi. Chi-squared. You don't want to call it chi because then everyone knows that you don't know what you're talking about. I know, busted. Chi-squared. There. Okay, but in general, the chi-squared is going to look something like this. So just the general shape of a chi-squared. If you have low degrees of freedom, it's going to be smushed up against this y-axis and it's going to be kind of sharp. Okay? But in general, the general shape looks like this. So this is the general shape. That's skewed, right? In fact, it's skewed to the right. And so here, this is when chi-squared is equal to 0. Right? And then chi-squared is increasing as I move further and further out. So our table behaves the same way as the other table that we were using, the Z table or the Z star line on the T table. Technically, I know it used to drive me nuts. So I had this this stats prof when I went to school, and I always complained that she just knew too much because I felt like I was asking a straightforward yes or no question, and she would say, yeah, well, except, and then she would just go into all the exceptions. And now I feel like I do that a lot. Like, well, in general, it's this, but there's exceptions. Anyways, and so let's see here. So the general shape, let's assume maybe for this, and maybe I'll put it down here. Let's assume degrees of freedom equals 4. We did briefly touch on it, but the degrees of freedom is the number of categories that you have minus 1. Okay? And it's on your formula sheet, so it's not too bad. But you do need to remember what K is. K is the number of categories. And so here, K is the number of categories. So by reverse engineering, if I say, let's assume that I have 4 degrees of freedom, then I must have 4 plus 1 categories, so 5 categories. That's a lot of things I want to compare, right? And remember, the idea is, okay, now I have more than 2 proportions that I want to compare, or counts even, to each other. And how well do they fit a hypothesized distribution, right? And so that's where the goodness of fit testing comes in. What's nice is we're only doing a hypothesis test, so there are no confidence intervals because we can't really build an interval if this distribution is skewed. And so we don't do that. But what does the table give us then? If we assume we have 4 degrees of freedom, I'm stuck on this 4 degrees of freedom line. And it behaves the same way that the other table did, except now the upper tail is the p-value. So we don't have a one-sided or a two-sided, because here there is no tail, right? And so our p-value is just going to be the area in the upper tail. Okay? And so how this works is when chi-squared is 7.78 at 4 degrees of freedom, I have 0.1 in the tail. Okay? So here I am at 7.78. The table tells me, and I guess I have 0.1. I'll throw a 0 on there for good measure. 0.1 in the tail. I can move out to 9.49. Of course, it behaves the same. As I move out further into the tails, I get less and less area underneath the curve, right? And so the behavior is the same. And so here, let's do 9.49. This area is 0.05. And you can find more elaborate tables with more breaking points, but I find that this one is sufficient. Just a rough idea. It does limit me to 6 categories, right? I stop at 5 degrees of freedom. Of course, you can find a bigger table in the textbook or just online, but it'll suffice. So then we can move out 11.67. It says that the area in the tail is 0.02. And we can move out 13.28. The area in the tail is 0.01. And then finally, I'll move it out 14.86. The area in the tail is 0.005. Which means just any chi-squared at 4 degrees of freedom that's larger than 14.88, well, the area in the tail is less than 0.005, and that's enough, right? That's really small. In fact, what was the other, we kind of reverse engineered it, and this was the first time that we used the critical value approach instead of the p-value approach. So we can use this, and we can still use the p-value approach, right? Take my chi-squared that I calculated, which was kind of new and foreign, so I'm ignoring that part for a little bit. But I take my calculated chi-squared and I try to figure out where it would fall on this line, and then I can find a range for my p-value. Or what we introduced last day was if alpha, I'm just going to steal this copy. I know, rude. It's because I can. Let alpha be 0.05, which is our default anyways, right? The significance level of 0.05, if it's not stated, you're going to use 0.05, 5%, kind of industry standard. That's here, right? I'm going to force this area to be 0.05, which means that the critical value, which is different, and context will tell you, so it's different from the critical value in the confidence interval, right? We called it a critical value, that Z star in our confidence interval. In this case, it's a critical value in the sense that if my calculated chi-squared is bigger than 9.49, then I have enough evidence to reject H0, because anything after that point, the area in the tail is smaller. So it flips back to the p-value, right? But it's another way that we can kind of draw our conclusion. And so then the chi-squared critical is 9.49. And so we talked about that last day. And just a new way of doing it. Or not new, we could have done this for z's too, right? You could force the area in the tail to be the alpha level, and then if your z is bigger than that or kind of more into the tails than that, then you reject h naught. So if the calculated chi-squared is larger, right? That would put it, so once you pass 9.49, it's going to be larger than 9.49, right? And so then the area in the tail is smaller. And so if the calculated chi-squared is larger than the chi-squared critical, we have enough evidence to reject h naught. We have enough evidence to reject h naught. Whew, okay. Okay. We've got an example, so I'm gonna hold off, but the calculated chi-squared, so I give you the null hypothesis in general is that the observed distribution equals the expected distribution. So I have some idea of what this distribution should look like. It could be an even distribution, or in the next example, we're going to have kind of a hypothesized distribution that we're comparing to. And so that's where the goodness of fit comes from. And I'm just now kind of panicking. I think I recorded. What a day. Okay. Even remembered. So then how we calculate the chi-squared test statistic is we take the observed. Now this can either be a count or a proportion, which is kind of cool. The observed count is usually what we're working with, minus the expected count for that category. Then you square it so that you don't have any negatives canceling with the positives. They would add to 0 anyways, usually. And so you square it to make it all positive, and you divide by the expected count in each cell, and then you add them all up, and that's your chi-squared. Yeah. And then we need our degrees of freedom, which is the number of categories minus 1. Now, the number of categories doesn't change, right? For the question, you have a set number of categories, which means that once you've decided that you have 4 degrees of freedom, for example, you're stuck on that line and nothing else matters. Okay. So we're picking up here on Tuesday, which is today. I don't think we need this anymore. A little bit of practice just using the table, but what's the problem? What's my problem? I didn't give you 9 degrees of freedom, but we can grab a bigger table. Do I have it? I don't think I do. Oh boy. Can I just cheat? Oh, there's one. Copy from last day. I guess ignore that highlight. That's not the one you want. We have 9 degrees of freedom. It's just that it's from last day, when we had 10 degrees of freedom. So notice that chi-squareds don't behave the same way as z's. We had a pretty good intuition about z's. Any z more than 2 standard deviations away or standard errors away, we're going to reject h naught likely. In this case, chi-squared of 17 is not that weird. So that takes some getting used to. And so what we have is we have chi-squared calculated is 17. I have 9 degrees of freedom. And so I'm going to try to place this 17 along this line. Notice that it just increases as I move my way out. Which means that 17 is somewhere between those two values, which means that the p-value is somewhere between 0.02 and 0.05. We're used to reading these areas from right to left, right? Because they're decreasing as I move out, but I have to list them from smallest to largest. And so I'm going to spring for that one. Nice. Phew, I was right. Feels good. This is our code, which you can ignore. We're not using R. But of course, Excel can calculate the chi-squared. So let's see here. Where's my Excel? I'm pretty sure. You recently opened this. How about a blank workbook? Nice. What was I going to say? I'm pretty sure. It'll tell me, it'll come to me. I'm pretty sure, there it goes, that Excel is going to give me the area to the left because it always does. So I'm going to play around with it just for fun, I guess. Let's see here. How can I type in here? Come on. Sign in to edit and save changes. No, I don't want to do that. Why am I not signed in? All I had to do was click sign in. Weird. Okay. I'm going to, now I don't remember the Excel formula in my head, obviously, because you don't have to. Just all we need to do is we need to be able to trust that it exists, which it does, and just start with an equal sign and see what happens. At least that's how I Excel. I'm going to go with starting chi-squared dot dist. Looks like I have 2 options. Of course, you can play around with it, chi-squared dot dist, but if I zoom in here, well, I can't. It returns the left-tailed probability, so the area to the left. Okay, just as I suspected. It requires your x, so your chi-squared. It requires the degrees of freedom and whether it's cumulative, which is always true, right, up to and including that point. Otherwise, it's just at that point, but that'll be 0, so that's useless. So I don't know why they do that. But if I go back, another beauty caught my eye here. What's this chi-squared dot dist dot rt? Right-tailed, probably. That's because I know that, but let's look at it. Now it returns the right-tailed probability of the chi-squared distribution, which is actually the one I want. So let's try that. It only requires x, so your chi-squared calculated, and the degrees of freedom, and then it just knows that you want the whole area. That's going to be the same as 1 minus chi-squared dist of x with the degrees of freedom cumulative equals true, right? But I think this is a lot easier, so I'm going to go for it. let's do 17 is my chi-squared that I wanted to play around with. And we had 9 degrees of freedom in that example. Oops, return. And I get 0.048716, which feels pretty good. It is between 0.02 and 0.05, right? But now I know I can find the exact p-value. Save. Although I keep forgetting that I don't need to save it, I can just copy it. But old habits and all. I'm gonna crop this up. And I would recommend that you use the chi-squared.dist.rt. However, this would be equivalent to equals 1 minus chi-squared dot dist. Oh, sorry, it's not chi dot squared. It's an eraser. Chi-squared dot dist of x, which was 17, 9, and true, right? But you have to do that 1 minus if you're just using the chi-squared dot dist. But at this point, you know, you're kind of getting more familiar with these Excel functions, and so you can play around with them, and just they're going to give you the same results. Okay. Notice that the R code, although it looks scary, but I think that's mostly the font. It is basically the same, right? The probability distribution of the chi-squared when Q is 17, the degrees of freedom is 9, and the lower tail is false. I get the same exact probability. Nice. We got skills. Let's see here. Do the same thing. I'll bring in the, and now it's conveniently highlighted at 10 degrees of freedom from before. So that's nice. But now I have a chi-squared of 30. I like to throw a little chi-squared calculated on there just to emphasize that that's something that I've calculated as opposed to the critical value later. But if I have a chi-squared of 30 and I have 10 degrees of freedom, then 30 is somewhere out here, right? Just after, but that means the p-value is just less than 0.001. And we don't really bother with between 001 or between 0 and 001. We can just say it's less than at this point. And so I'm going to go for C. Nice. Probably not. Yeah, so this one is using the bigger one that's in the textbook, but then I have just grabbed, let's see here, on your formula sheet, I grabbed a mini version of it. So what we'll have is this, but I didn't keep 10 degrees of freedom, so it kind of is hard to do these questions with it. But I've just got a little mini version on there, which will be enough for the tests and stuff. Yeah. I just didn't want to carry around more papers is really what it came down to. But usually we would have, so traditionally we actually have a Z table and then the T table that we've been using and a chi-squared table and an F table. But yikes, no, I don't want to do that. So I've just boiled it down to 1.5 tables. Just a little half. But yeah, there is a big table with more degrees of freedom. It exists, but we don't need it. Besides for these examples, I guess. Okay. We can do the same thing in Excel, but I think we're ready to just round up. We did this example last day, right? Labby's dice. And so we had this idea that, okay, every face of the die should show up an even amount of times, right? If we roll it an infinite number of times. We didn't roll it an infinite number of times, but they rolled it, I think, 20-something thousand times. And so I'm willing to take that as basically infinite. And so the research question that we were dealing with was, do these data provide convincing evidence of an inconsistency between the observed and the expected counts? Now, what we could rephrase this is, are the counts of the die faces evenly distributed? So, or are the counts evenly distributed? That's another way that we could phrase this, which is usually how I would phrase it, right? Are the counts evenly distributed? So if I have 6 counts, I would expect each of them to happen 1/6 of the time, right? Depending on how many times I rolled, that's my expected value. So our null hypothesis is that there's no inconsistency between the observed and the expected counts, or I kind of prefer the next one, the observed counts follow the same distribution as the expected counts, or an even distribution. Our alternative is always going to be just the flip side of that for a chi-squared test. So that's nice. We don't have to worry about one-sided or two-sided, less than, not equal to, that kind of thing. And it is in words, which is, I would say, harder, but a lot of people like it better. But there is an inconsistency between the observed and the expected counts. The observed counts do not follow the same distribution as the expected counts, which would then mean that there's bias in which side of the die comes up. Now, we calculated a test statistic of 24.67, right? We had the observed counts of each of the faces, and we had the expected counts of each of the faces. Let me see if I have it here. Let me go grab it from last day. Where am I here? Page. So this is last day. From last day, we had the outcome. So each die face, right? We rolled it a total of 315,672 times. And we observed each of these for each of the faces. Relatively even, just kind of eyeballing it. But then what we did was we took this 315,672 and divided it evenly because that's my hypothesized distribution, right? And so divided by 6 gives me 52,612 for each of these, right? So my expected counts, oops. For an even distribution, we said, okay, that should be 315,672 divided by 6, which if they did any rounding, I actually don't want you to round, but I think it's because it's a lot of numbers. 315,672 divided by 6. Oh, phew. It is an even number. That was really nice of them. But don't round. Don't round if you get a decimal. You keep it as the decimal because it's just the expected count. We've seen expected counts before, right? When we were talking about proportions, and that makes sense because this is just an extension of not just one proportion compared to 1/6, right? Or two proportions compared to each other. Now I'm extending it, and that's really all I'm doing it is I'm extending it to 3 or more proportions, comparing them to each other. Right? Okay. Now, this, of course, came from here. So I take my observed total and I split it the way I hypothesize. And in this case, an even distribution is what I hypothesize. And so that's why they're all the same expected count. Then next to it, it's work and it's tedious, but it's not hard, right? You just kind of need to get into the groove of things and take the observed count minus the expected count, right? The observed minus the expected, then square it, and then divide it by the expected count. And then you get a number. Then you take all these numbers and you add them up, and that's your chi-squared. That's the sum of these values. And so here, I want to say that this is, the chi-squared is the sum of the observed minus the expected squared over the expected. Right? Add up all those numbers. Okay. Now what? I've kind of fake stated our null and alternative hypotheses, right? Because we already did it last day, and we already did this step 2, which is calculate the test statistic. How about we need to find the degrees of freedom? Because I need the degrees of freedom to use the table. Whether I use the critical value approach or the p-value approach, it doesn't matter. I still need to know the degrees of freedom. The degrees of freedom from your formula sheet is k minus 1. In this case, I'm comparing k equal to 6 groups or categories. And so k is 6. So the degrees of freedom is 5. Convenient, because that's what I have on my mini table. And so let's see if I still have it. Oh, I have to go grab it. Copy. So on our mini version here, I've decided, okay, I have 5 degrees of freedom. That's not going to change. So we can use, let's practice the critical value approach. The critical value if alpha is 0.05, because I don't remember them saying to use anything else, then I would say, okay, 0.05 is my upper tail area. Then my chi-squared critical is 11.07. Remembering the shape of the chi-squared, okay, then I force the area in the tail at 11.07 to be 0.05 or vice versa. So then if I pass 11.07 with my chi-squared, then my tail area is less than 0.05. So since my chi-squared calculated, which was 24.73, and I think there's a typo actually here. Hey, what the heck? Hopefully I have the same color, basically. Doesn't matter. So my chi-squared calculated is 24.73. So I have, oops, my chi-squared calculated is 24.73, which is greater than my chi-squared critical. And you can say it in words. You don't have to use the inequality. But because my chi-squared calculated is larger than the critical value, then I have enough evidence to reject H naught. We have enough evidence to reject H naught in favor of HA. Which means that they are not evenly distributed. Therefore, and we just reword the question as an answer. Do these data provide convincing evidence of an inconsistency between the observed and expected counts? Yes, it does, right? Because we rejected H naught. Or the counts are not evenly distributed. Therefore, the counts are not evenly distributed. This is the using the critical value approach. But let's also do the p-value approach. So now same thing, but using the p-value approach, which is the one we're more familiar with. Copy this. Paste. Okay. I still have 5 degrees of freedom, and I calculated my chi-squared. Calculated was some version of 24.73. Let's be consistent. Okay. So now I'm going to take my 24.73 and I'm going to place it on the table, but that's somewhere out here. That's okay. What does that mean? So it's somewhere here. And so therefore, the p-value is less than 0.005. Very small. We can use software too, but feels like overkill to solve it 3 different ways. And so you can try it with software, but your conclusion is since the p-value of 0.005 always want to show off that you can tie everything together. You don't just want to do a generic, the p-value is less than the alpha level. You have to show me that you know what the p-value is and what the alpha level is and what that means. So since the p-value of 0.00, or maybe I should say is less than, that's what I should say. Since the p-value is less than 0.005, it is also less than 0.05, the alpha level. It is also less than the assumed alpha level of 0.05, which means we have enough evidence to reject H naught. Which means we have enough evidence to reject H naught. And we should probably say in favor of what? In favor of HA. Therefore, the counts are not evenly distributed. Therefore, the counts are not evenly distributed. Same conclusion, just two different paths of getting there. It's kind of a choose your own adventure on the test. If you prefer the critical value approach, as long as you follow through and you state your conclusion based off of the critical value approach, that's fine. Or the p-value, doesn't matter to me. I will know them both, and that's okay. So you're welcome to use either approach on the test. Maybe I should write a note about that. If you prefer, you can even use the critical value approach with the Z table. There's no harm in that, right? As long as you follow through. So if you prefer it, which I do find a lot of people prefer it, but I need to teach you about p-values. So if I teach you the critical value approach first, then you'll just kind of cling to that. But I need you to know about p-values. So that's where I start. But you're welcome to use either approach on the test. Just a plural. Got a test and the final exam, of course, where we'll be doing more. We already did this, so I'm going to skim through it. Finding the p-value, blah, 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 blah. And we already said our conclusion. And so there's kind of some background on why that's the case. I guess the 1 to 6 axis is shorter than the other two. Let's talk about the conditions. So you can read up on that if you want, but that's not what I'm interested in. The conditions for the chi-square test are relatively simple because we're used to kind of rigorous conditions, right? I have to have a random sample and my sample size has to be less than 10% of the population. And if I have more than 2 samples, then that has to be true for both. Or if I have 2 samples, it has to be true for both, and they have to be independent of each other. And I have to have at least 10 expected successes and failures, and I have to have at least 10 observed successes and failures. Boy, for 2 sample proportions, confidence intervals, and hypothesis testing. So then, switching over to chi-square test, this is kind of breezy, right? For independence, each case that contributes a count to the table must be independent of all the other cases. Fair enough, right? And so, especially if we're rolling a die or something like that, we can assume that they're independent of each other, right? Rolling a 6 doesn't affect the probability of rolling a 6 again. right? And so by definition, they're independent. There's a sample size condition, which is new. Each particular scenario, so cell or count, you have to have at least 5 expected cases. Now, in this table here, whoa, yikes, here, what you would need to check is to make sure that each of these is more than 5. I'd say we're safe, but sometimes if we have a small sample size, then that's not necessarily true. For us, it'll always be true, but it's something we have to keep track of. Because I can't pick up on kind of small expected counts. And so I need to have at least 5 expected cases. That one's the only new one, kind of a curveball, something to keep track of. I have to have more than 1 degree of freedom. If we think about it, well, if the degrees of freedom is k minus 1, and I need degrees of freedom to be greater than 1, then to be greater than 1, then k must be greater than 2. All right, clean up this k. Wait. Why? Because if I have k equals 1, that's a 1 sample proportion type of question, right? And I could have looked at that table and said, okay, I can compare the count of 6s, that proportion, to 1 over 6. I can do that, right? And so here, since if k is equal to 1, then I have a 1 sample proportion question. And if k is equal to 2, you guessed it, I have a 2 sample proportion, right? If I have 2 groups, I would just treat it as 2 sample proportions and use the Z distribution, which is kind of arguably more powerful than the chi-squared. And so then I have a 2 sample proportions type of question. So that's fine. You don't even really need to check this condition, because if you've decided it's a chi-squared goodness of fit test, right, then how you got there was you had more than 2 proportions that you wanted to compare to each other, or more than 2 counts. Okay, so that's nice. How about another example? Now, in this example, I do not have an even distribution for my hypothesized distribution. And so here, and the reason I'm highlighting this is because there's an assignment question where there is not an even distribution, and people always text me and say, how am I supposed to deal with this? Like this. So here, this is an example of when the hypothesized / expected distribution is not evenly distributed. We can even use current election results, right? There were polls. I got so many texts from Sarah, or whatever her name is, Beth, or they use different names. I don't know why. We all know they're bots, but makes us like them more, I think. Right, and so they have some polling results, some pre-voting results that we could compare to the actual results, right? Our observed results. In this case, we have, if I had my wits about me, I could have changed this to be more about our election, but who knows? And so in this case, in the 2009 Iran election, I guess there was talk of election fraud. I was unaware. I was finishing my undergrad in 2009, so I was a little busy, I guess. And so what we're going to do is we're going to compare the data from a poll conducted before the election, and we're going to call that the little switcheroo here. Usually, the actual results of the poll or at a vote would be our observed results. But in this case, kind of extreme, because they're talking about election fraud, then we're going to use the poll conducted before the election as the observed data. It's kind of backwards, but and then we've got the reported votes in the election to see if they follow the same distribution. Okay, so we've got 3 candidates, or I guess we have 2 main ones, and then we have a lump of minor candidates. And the observed number of voters in the poll was 338, 136, and 30 for a total of 504. And then we've got the reported number of votes in the election as a percentage, which should add to 100 as well. And so we're going to treat the poll as the observed and the reported kind of percentage of voters in the election as the expected distribution. And what we want to see is, do these values follow this distribution? So our null hypothesis is going to be that the observed counts from the poll follow the same distribution as the reported votes. And then your alternative hypothesis is just the flip side of that, right? That they do not follow the same distribution. And so that's why on your formula sheet, I just have, what does it say? Well, the observed distribution equals the expected distribution. I do want to see a little bit of finesse here, right? The observed distribution from the polls is the same as the expected distribution from the vote, or the reported from the vote, or something like that. Kind of question specific. So we've got our null and alternative hypotheses. This is step 1 in our hypothesis testing. If you like to break it down by steps like I do. Step 2 is calculate the test statistic. Okay. Which means I have this percentage distribution, right, across each of the candidates. But what I can do is I would expect out of 504, I would expect 63.29% of those here. So I'm expecting 319. And then I take my 504 times 34.1, and I'm expecting 172, and then I'm expecting 13. Of course, they should still add up to 504. Then, usually I do it in the table next to it, but it would make kind of a tight table. And so each of these categories, kind of some foreshadowing here, K is equal to 3. Right, I've got 3 categories that I want to compare to each other. And so that's one of the conditions for the chi-squared satisfied already. What's the other condition? Well, my observations have to be independent of each other. Not necessarily true, but it is something we're assuming here, right? And I need at least 5 expected counts in each category, which I have. 13's small, but big enough. So if I take the observed minus the expected squared over the expected for candidate 1, right, I get a 1.13, and I do that for both of these, and then I add them all up, I get a chi-squared calculated of 30.89. So chi-squared calculated is 30.89. Whether you prefer the critical value approach or the p-value approach, I'm going to let the next slide determine which approach I'm using, probably the p-value. Okay. It is using the p-value, so I'll use the p-value approach. But I'll add a page here. I'm hoping it'll paste the table, but I'm not 100% sure. And now it's hung up, not showing you score. We said, and we've done the little calculation in the subscript, which is pretty common to put the degrees of freedom in the subscript of the chi-squared, because it is the thing that determines the shape of the chi-squared. And so we said k is 3, so my degrees of freedom must be 2, which matches here. And so if I go to my table, then I get my chi-squared calculated of 30.89 is somewhere way out here. That's okay. So then it's just less than 0.005. And I'll say the p-value is less than. I shouldn't do my lasso around there. Okay. So my conclusion then, my p-value is less than 0.005, which is very small, but we could have used the p-value approach and said, okay, let's assume an alpha level of 0.05. Well, any chi-squared bigger than 5.99, I'm going to reject H naught, which, right, 30.89 is bigger than 5.99. So step 4 is the conclusion. And this was step 3, I guess. Step 3, find the p-value. Get so impatient with the slides though. So since the p-value, oh, things went dark here. Hopefully it doesn't mean anything. Since the p-value is less than 0.005, it is also less than our assumed alpha level of 0.05. Also less than our assumed alpha level of 0.05. Don't let those zeros get you, right? 0.005 is less than 0.05, which means we have enough evidence to reject H naught. In favor of HA. What can we conclude? That means that our observed votes didn't match, or sorry, our polled votes didn't match what we had reported in the election. That's not that rare, actually, but it is one way to say, okay, well, these two things don't really match each other. I would be curious to know how our polling results compared to our actual results. So maybe I'll dust that off and see. But therefore, there is evidence of, I was going to go extreme. but therefore, ignore this. And then I just reword the alternative hypothesis, because if I reject H0 in favor of HA, then the observed counts from the poll do not follow the same distribution as the reported votes, which indicates voter fraud or whatever they're calling it, but that's okay. And it's one of these, I guess the first one. I don't want to read them all. I'm too lazy. Because we just did it anyways. Okay. I feel like if they hadn't reset the clock, you guys would be, well, you would have left. Probably. I hope. I told you one time I taught a summer course up at UBCO. And so the lectures were 3.5 hours long, twice a week in the summer. It's intense. And one time I forgot to give them a break because I just can talk forever about all these things. So it can happen. But no one really indicated that I had run out of time or they needed a break. So I blame them. Those guys. So it can happen. Okay. Any questions about the chi-square goodness of fit test? Okay. How about a chi-square test of independence? What's going to be the difference between these two? Now, the difference between these two, the chi-square test of independence is if we have a table like this, where I have some variable 1 and some variable 2. We've seen this before, right? Off the top of my head, I can't think of an example. Oops, I wanted to select that, grab it. For example, it's going to look like this. No, it's too sad. The manatees, it is from the test. That's the contingency table. So we're going to have a contingency table. I'm trying to think of a more fun contingency table. How about male and female manatees? The gender of the manatee and how about their favorite food? For simplicity, they only get 3 different types of food. What can they be? Let's make it lettuce, tomato, bacon. No. Although that would be funny. What, cucumber. I happen to know they like lettuce a lot, and that's usually what they get. But okay, so this looks familiar, right? This is a contingency table. Now I have 2 categorical variables, right? And so here I have 2 categorical variables. Each variable has some number of categories, right? And so here, failing to remember what, can I just cheat? Well, I don't call them anything. That's how I don't remember. But we have some number of rows and some number of columns. And we're going to have some counts here, right? The males that like lettuce, the males that like tomato, the males that like cucumber, the females that like lettuce, the females that like tomato, and the females that like cucumber. This is all familiar at this point, right? Overall totals, this is, of course, the males that like lettuce plus the males that like tomato plus the males that like cucumber, making for the total males. Same thing for the females. What are we assuming? We have to assume that they can only have one favorite food, right? And we're also assuming they're only one gender, which is true for manatees. And so now my totals would be the females. And then in the rows, or sorry, in the column totals, I would have the ones that like lettuce, the ones that like tomato, and the ones that like cucumber, and a grand total of N manatees that we've surveyed. Not surveyed in the sense that we asked them the question, but that we've observed and we have some counts from. Okay. Now, so this is going to be your telltale sign that it's going to be a chi-squared test of independence. You can talk yourself into, okay, I have two categorical variables and I would have to give you a table, right? A contingency table like this. And so then you're going to think, ah, dang it, it's a chi-squared test of independence. But at least you'll know, right? You'll know why, dang it, in a little bit here. It's a little bit more work. Not too much, but a little bit. Okay. But what we want to know, the chi-squared test of independence is going to test whether the gender of the manatee is independent of what their favorite food is. Right? And so the test of independence is going to test, are these two categorical variables independent of each other? And so here we test to see if the two categorical variables are independent of each other. And of course, I'm going to highlight that independence because that is what we want to find. Okay. How about I introduce from the formula sheet. Look at us, we're just ripping through this formula sheet. Feels pretty good, right? Well, I think so. So the chi-square goodness of fit test is when you have just some counts, right? Some number of categories that you want to compare to some observed or hypothesized distribution, right? You have some idea of how these things behave, whereas a chi-square test of independence, you'll have a contingency table. I have to give you the contingency table. Okay? If I'm super mean on the assignment, but not on the test, because I'm not mean on the test, you've got enough going on the test. But on the assignment, I might give you some key counts and then you can generate the table. That's mean. I don't want you to do that on a test. I might get you to do it on an assignment. I really can't remember. Okay. The chi-squared test for independence on your formula sheet looks like this. Now, your null hypothesis is that these two variables are independent of each other. Obviously, the alternative is that they are not independent of each other, right? Which is what we said here. Fair enough. That's not the hard part. The hard part is finding the expected count in row I, column J. Okay. And so here, this is the expected count in row I, column J. You're going to take the row total, times it by the column total, and divide it by your grand total. Now, to find the expected counts, I personally like to just make a duplicate of the table with my expected counts. Okay. Or you can do them side by side. But I'm going to say we duplicate the contingency table and find the expected counts. And find the expected counts. So I am going to nab this. Paste. So I can delete that. And clean this up a little bit. Too much activity on here. How about that? Okay. I am going to just call this N down here. That's my total number of manatees. N. These are my row totals. These are my column totals. And this is my grand total. Using the same terminology as here. Yeah. Okay. Once we get the hang of it, it's not too bad. But don't go cross-eyed, okay? What's this going to be? I'm going to erase properly there. And now my expected counts. Are going to look like this. You take your row total, right? So from the formula sheet, you take your row total for that cell, times it by the column total, and then divide it by the grand total. So for each of these, if we move methodically, right, the row total times the column total divided by the grand total, I get M times L over N. Now I'm multiplying here, and that's not obvious because M times L. Because before we just had ML representing the counts of the males who preferred lettuce, which is different from M times L, I'm sure. How different? We'll find out with our hypothesis test. Okay. Moving on to the males that like tomatoes, I would expect to have M times T over N in that cell. Bless you. M times C over N. Then we do the same thing for the next row, right? F times L over N, F times T over N, and F times C over N. That would be the distribution if they're independent of each other, right? So that's how we get the expected counts, and those are the values that you're going to compare to the observed counts. So a little bit more work. What I find is once I introduce this, everyone wants to use this formula for the goodness of fit, but then you don't have a row and a column, you only have one of those, so it doesn't work, right? So just keep track of how you find your expected counts. Once you have your expected counts, though, our chi-squared stays the same. We take your observed count in each cell, subtract the expected count from that cell, square it, and divide it by the expected count. And then you add those all up and you get your chi-squared. Right? And so once we have all the expected counts, what am I going to interject here? Make sure they're all greater than 5. That's one of the conditions, right? So we may as well check that they're all greater than 5. Make sure they are all greater than 5. Then use those to compare them to the observed counts. So then use the expected counts to calculate chi-squared. Chi-squared is the sum of the observed minus the expected squared over the expected. Notice how I've dropped it's sloppy. I've dropped the subscripts, but I find that the IJs are kind of confusing when we're first starting out. So you can drop them as long as you remember to do it to every cell, which is really all those subscript IJs are saying. Do it for all of them, right? And then add them all up, right? Then you can drop the subscripts. That's fine. Then now we're back to this chi-squared, which is not super familiar, right? I'll do a better chi-squared. It's supposed to be a fancy X. Once I have my chi-squared, I know I can use my chi-squared table, but I need my degrees of freedom. And luckily, the degrees of freedom on your formula sheet is what? Number of rows minus 1 times the number of columns minus 1, right? But you're multiplying in here. This is where I thought maybe I had used something crazy like M minus 1 and N minus 1, which is kind of common, but I hadn't. So I just have the number of rows. That's okay. Is the number of rows minus 1 times, and I'll highlight that here, times the number of columns minus 1. In our case, right, as from the manatee example, the degrees of freedom, I have 2 rows, 2 minus 1 times I had 3 columns, 3 minus 1, 2 minus 1 is 1, 3 minus 1 is 2, 1 times 2 is 2. Sold. Now I know how to use the chi-squared table. Now this chi-squared behaves like the other chi-squareds, and I have 2 degrees of freedom. And so from here on, right, we're kind of back to what we were just doing with the goodness of fit test. It's just how we got to the chi-squared is slightly different, and how we got to the degrees of freedom is slightly different. Since we don't have numbers, and I'm not very good at coming up with numbers that will work on the spot for the manatees, how about we use this example? Popular kids. So students in grades 4 to 6 were asked whether good grades, athletic ability, or popularity was most important to them. And so a two-way table separating the students by grade. So that's a categorical variable, right? 4, 5, 6. And by choice of most important factor is shown below. Do these data provide evidence to suggest that goals vary by grade, right? Or does knowing the grade tell me something about what they prioritize as being most important? And so here, first thing we want to notice, I suspect I'm going to have to do a chi-square test of independence because I have been given a contingency table, right? And so that's our first step. Once we've determined that it's a chi-squared test of independence, then we stay there on our formula sheet and we don't move. So I hate these tables, mosaic tables. Ugh. But we can look at them to determine if there's a difference, but just ignore it. Don't look at it. No, you can look at it. I just don't like them. And so we've got these observed counts, right, for each of the grades and what they prioritize or what they think is most important. And so first thing you might need to do, because we know we're going to need the totals, right? I'm going to need the row totals, and I'm going to need the column totals, and I'm going to need the grand total. And I hope that they did it. Okay, they kind of did it. Should we just do it? And then, no. No. I said no. We're not going to do it. Okay. No, we're going to do it. We can do it. We'll do it from start to finish. And then the rest of the slides, we'll do it, but kind of in a weird sprinkly way. So I don't like that. All right. How about I clean this up and I grab first, the type is going to be a chi-squared test of independence. As you can probably tell by now, a huge hurdle on the test and on the final exam, because then we'll have even more types, is figuring out what type of question it is. Once you've landed on that, then you can just kind of follow the formula sheet and let it guide you, right? And so that's arguably the hardest part. And sometimes, if I'm nice, I make it worth 1 mark where you tell me what type of test it is or what question type it is. I haven't decided. Okay, let's do a full-on hypothesis test, which means that step 1 is to state the hypotheses. Bless you. from the formula sheet, and I'm gonna need to paste this. I can't wait for my my iPad to know what I'm thinking, and then I don't have to switch between settings. I think it's gonna happen pretty quick. I find that now I get kind of fed up with AI. I'm like, it's supposed to be better than this. I expect a lot, I think. Fine, now we have AI. Make it work for me. Like my phone knows how much gas I have in my car, and it knows where I'm going. So why wouldn't it warn me that, hey, you should probably stop for gas? Just a thought. Or I can be an adult and just know that I need to stop for gas. The variables are independent, kind of cryptic, yeah? But we're gonna rephrase this in terms of the question, right? The variables are what grade they're in and what they prioritize, or kind of what they think is important, most important. Do these data provide evidence to suggest that goals vary by grade? I'll be more explicit than that, I guess. The null hypothesis is that the grade level and what they find is important and what students think are important, students think is important. The grade level and what students think is important are independent. Wow, what a mess. I'm gonna go for it. Are independent of each other. This is where we get into the stuff where everyone who is really pumped for a math course, it's like, I didn't sign up for this. It's terrible. I know. The alternative, though, is just the flip side of that. So the alternative hypothesis is that the grade level and what students think is important are not independent of each other. Stating our null and alternative hypotheses. That's step one. Step two, mostly because we don't have the expected counts yet. You could have calculated them kind of before starting and checked the conditions, but we also have relatively few conditions, and so I'm not too concerned. The conditions are each of these counts, right? They all have to be independent of each other, right? You're either in one of these grades, and we assume they can only have one thing that they prioritize, right? So they're independent, but then also the expected counts have to be more than 5 in each cell. That's still true for a chi-squared test. So step 2 is calculate the test statistic, or I call it do the test. Do the do. Okay. To find the test statistic, I need the expected counts. Okay. Now, how I was raised, academically raised, was like this. I can have my totals here. We just used to write the expected count kind of around the observed. So then you can see 63 minus the expected squared divided by the expected. And you can kind of more easily do the math that way. That's kind of difficult, I guess. And so for this one, I'll write out a new table, but you're more than welcome to just kind of jot down the expected counts somewhere beside each of the observed counts, and then you'll have them linked up. And it does make it a little bit easier later on. But first we need the totals. 63 plus 31 plus 25 means 119. In fourth grade, 88 plus 55 plus 33, 176. We're in fifth grade. 96 plus 55 plus 32 is 183. Adding those guys all up, 183 plus 176 plus 119, I get 478 students in total. Hopefully, these totals also add to 478, but let's check. 63 plus 88 plus 96. And this part is just tedious, not hard. 31 plus 55 plus 55. 141. Whoops, 25 plus 33 plus 32. 90, just double check. 90 plus 141 plus 247. 478, what a relief. They have to add to the same thing. Okay. Now my expected counts. I'm gonna do this, and I'm gonna do something sneaky. Just color it white. That's sneaky. Nice. The expected count in this first cell is going to be the row total times the column total divided by the grand total. So I get 119 times 247 divided by 478. Now this is where it becomes important that you don't do any rounding. You want to keep the decimals, or as many as you can. 119 times 247 divided by 478. 61.49. Let's keep at least 2 decimal places. I'll show the math for just a few more, but then I'll just kind of rip through and calculate the expected counts. And so 119 times 141 divided by 478. Oops, I said I was going to write it down, didn't I? I get 35.10. I'll do this one. 176 times 247 divided by 478. 90.95. And then if we kind of hit the gas here, 119 times 90 divided by 478, I get 22.41. 176 times 141 divided by 478, 51.92. 76, boring, times 90 divided by 478, 33.14. last 183 times 247 divided by 478. 94.56. And maybe, just maybe, you're thinking, wow, I can't wait to set up these calculations to be done automatically in Excel. You'd be right. But it can even do more fancy things, like just take a table and calculate the expected values behind the scenes and just spit out the chi-squared. That's kind of cool. I get 34.46. Okay. I'm gonna have how many 3 by 3? 9 different, ugh. And this is what I mean. You say, oh, I know it's a chi-squared test of independence. Oh no, there's so much work. All right, what do we want to do? We want to see how far is 63 from 61.49, right? Essentially, that's what we're doing. We're seeing how far is 31 from 35.1, but simultaneously, right? And so to do that, we need our chi-squared. And I'm so tempted to Martha Stewart this thing, and I might still. What does Martha Stewarting mean? Just pull it out, baked. There. Chi-squared is the sum of the observed minus the expected squared over the expected. Which means it's going to be the observed 63 minus 61.49. Okay. Square it, divided by 61.49 plus, onto the next cell, 31 minus 35.10, square it, divided by 35.10. Can I cheat from here? Sneaky. I'm gonna steal it. Look at this. Copy from way later in the slides. Hey, even they cheated. And you get the idea. Our chi-squared, our calculated chi-squared, 1.3121, just itty bitty. Depends on the degrees of freedom though. So step 3 is usually find the p-value or the critical value if you prefer it. Ha, I can do it. Okay. So from our table, we use the same table, which is on your formula sheet. Hopefully, yeah, it works. We need our degrees of freedom. It's the number of rows minus 1 times the number of columns minus 1. Can I do that? We had 3 rows and 3 columns. So I have 3 minus 1 times 3 minus 1, which is 2 times 2, which is 4. So I have 4 degrees of freedom. regardless of if you're using the critical value approach or the p-value approach, we're not going to reject H naught either way, right? And so step 4, or I'll say the p-value is greater than 0.10, right? Because 1.13 or 3.1? 1.31 is somewhere over here. Not even close to 7.78. That's okay. Just means we don't have enough evidence to reject H naught. So step 4. Oh, what's one thing I forgot to do? I forgot to run through these and make sure they're all greater than 5, which they are. So that's good. Phew. So we're allowed to proceed, which I already did. Your conclusion, I'll use the p-value. Since the p-value is greater than 0.10, it is not less than the alpha level. It is not less than, I'll say, the assumed alpha level, because I don't think it said what to use, of 0.05, which means we do not have enough evidence to reject H naught, which means we do not have enough evidence to reject H naught. What does that mean for the students, the grade levels, and what they think is important? It means that what they think is important doesn't matter what grade you're in. You're going to kind of feel the same way throughout the grade levels. Or knowing what grade they're in doesn't tell you what they think is important, right? And so I'm going to just grab the null hypothesis and use that as my conclusion, because I didn't have enough evidence to reject H naught. So, and maybe undo, which was this. Therefore, the grade level and what students think is important are independent of each other. Now, we kind of check the conditions. As long as you know what they are, it's okay. These slides just go through and do the exact same thing that we did, blah, 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 blah. And that's the end. I'm all out of slides. This is the end of chapter 6. How about them apples? Which means we're going to start chapter 7 next day, which means we're going to move into numerical data. But we're going to do confidence intervals and hypothesis testing again. Don't you worry. All right. If you have any questions, let me know. Otherwise, see you Thursday.